All right, well, welcome everyone. My name is Melissa RC, and I will be the webinar moderator for today's event. Welcome to the second masterclass series webinar of OMS eLearning Academy. Today's webinar topic is MCOR strategy to manage refinery offsite operations. We have an overwhelming response of 100 plus registrations from 30 countries and welcome you all and hope that you all will have a very informational and interactive session today. Before we get started, I would like to go over a few house rules. The webinar will be about 45 to 50 minutes long with 10 minutes for Q&A session. You can enter your question in the chat box during the presentation at any time. These questions will be answered at the end of the presentation. Please change your question settings for everyone so everyone can see them. The webinar will be recorded and available on the OMS eLearning Academy website. There will be two poll questions at the end for your input. We do ask that you please give us your candid feedback at the end via the redirected Google form. We will also send a complimentary gift of 250 plus pages of an ebook of 19 published articles by Dr. Agrawal to your registered email. In case we don't have your email address as provided by LinkedIn, you can mention it in your reviews. Today's webinar speaker is Dr. Suresh Agrawal, the founder and CEO of Offsite Management Systems, LLC. An Academy Director of OMS eLearning Academy. He has a bachelor's degree from IIT Mumbai and a PhD in chemical engineering from IIT Chicago. He has more than 40 years of consulting and refinery automation projects for refineries worldwide and has published 30 plus papers in his areas of expertise. Offsite Management System LLC was founded in 1998 in Houston, Texas. It is chartered to provide consulting and refineries automation projects executions worldwide. OMS eLearning Academy was founded in 2018 to provide continuing education to professionals working in downstream refining industry and related businesses via the eLearning platform. The Academy has 200 plus courses that can be taken online at any time, anywhere, and on any device. With this, let me request our speaker, Dr. Agrawal, to start the webinar. We'll be back at the end of the presentation to dismiss you and ask you to do the polling questions. Thank you so much, everyone, and welcome, Dr. Agrawal.
Thank you, Melissa. Greetings, everybody, and thank you for joining us. In some of the countries, maybe late night, but just be with me. You'll have a very informative webinar today. So what we're going to do, we're going to define on-site versus off-site operation in refinery. Define MCOR, MCOR of refinery operations. How does MCOR affect the bottom line? And we'll discuss each MCOR strategy elements for efficient and effective operation. Then we'll also touch upon how to estimate tangible benefits. What are the methods? And in the end, will emphasize the investment in human capital, which is a key to the profitable refining industry. So let's just for the completeness, recapture the concept of on-site versus off-site operation. The on-site operation basically relates to the process units which manufactures different components, different products from the crude unit. It focuses mainly on safety and component qualities in operation optimization. It does not make any end product which can be sold to the consumers and businesses alike. On the other hand, offsite operation manufactures end products like fuels and other end product which can be sold directly to the end users. It controls inventory, it transfers material and receives feedstocks and dispatches products. So this entire envelope consists of many activities and many infrastructure related items, which is labor and offsite operation. So what does MCOR stand for? MCOR stands for manage infrastructure, control manufacturing, optimize production, and reconcile hydrocarbon. This is a term that my company developed and defined in terms of operation. Now, this MCOR term is not only offsite operation, it's actually defines the entire refinery operation. But it has a different impact for on-site versus off-site. So in this slide, I have shown each category, how much do they affect. If you look at manage infrastructure, it is more towards the off-site operation because off-site has a lot of infrastructure like tanks, pumps, valves, and you may call it. But infrastructure doesn't really mean hardware like a touch and feel. It also includes control systems, databases, and many other items which we'll touch upon later. The second item is control manufacturing. Now, control manufacturing is somewhere in between on-site and off-site because on-site is also manufacturing and the control is a prime objective of those process units. Optimize production. It has some degree on the on-site operation, but it has towards more of off-site because end products are manufactured in off-site operation and they need to be optimized for maximum gain and minimize giveaways. In the end, the reconcile hydrocarbons. This is the area where all input and output and everything as in the refinery reconciled in terms of what they have got, what they have lost. It is more as the operation of off-site operation, not so much of on-site. On-site has some little bit reconciliation, which we'll discuss in later slides. So if you look at it, 4 aspects of MCOR: manage infrastructure, control manufacturing, optimize production, reconcile hydrocarbon. You can see that effectiveness of infrastructure varies from reconciliation to manage infrastructure, while the efficiency and profitability increases from infrastructure to hydrocarbons. And if the infrastructure is not effective in terms of its completeness, also in its automation, then it affects the efficiency in next 3 phases of control, optimize, and reconciliation, and hence the profitability is also affected. And we'll discuss each of them in more detail. So the downstream refining have challenges in each of these MCOR systems: manage, control, optimize, and reconciliation. In terms of management, it's challenging to handle large number of field equipment. Manpower is very manpower intensive. Calibration of meters, regular maintenance, analyzers, and we don't have enough shared equipment which causes a loss in production. In terms of control, if it is not robust hierarchically designed, then refineries start losing money. Training is not adequately provided to the staff, no integration, outdated control systems, mixed bag of multiple and redundant software vendors, and performance tracking lacking. When you go to production, optimize production, it challenges for the suboptimal blend recipe, misbalances inventory, quality giveaway. Crude quality vary and must be blended to design specs. Blending models are not linear. Non-linear, must be carefully programmed. Performance feedback. In terms of reconciliation, misaligned fence line balances, order received and execution, many streams and interfaces, procedural nightmare. So these are the challenges of the refinery faces every day. And I have touched upon this more in detail my previous webinar, and recording available on our site. You can view it again. So let's look at each of the area, how to manage infrastructure. Now, infrastructure consists of tank farm, which is maybe 100 to 400, depends on the capacity of the crude refining. Field equipment, material movement, discrete and online analyzers, sampling system, terminal racks, pipelines, control system, servers, anything which is required to operate the refinery is it's grouped under infrastructure. And you can see from this slide, it's just not the hardware only, it's the control system, databases, procedures, workflow. So this all is under management of infrastructure. Let's go a little bit more in detail. Let's look at the tank farm management. What does it require? We start with a single tank gauging system, which measures the level, pressure, temperature, water level, and density. And then it goes to the tank farm for a tank information system where it monitors the inventory of each tank and then for the entire tank farm system. And it does the temperature compression of custody transfer on mass basis. Now we all know that when we sell products to the customer, we don't sell on volume basis, we sell it on the mass basis. And for that, the temperature compression for 15 degree have to be brought to the same standard. And this is necessary for custody transfer. Then the second part of the management of infrastructure comes the material movement, which is also called oil movement. Now, oil movement has two areas, moving from tank to tank or from different source or different destination. And it can be moved as either a fixed path, it means the path of transfer are predefined, or it can be dynamic path, depends upon what is available the time of transfer from the source and destination, it moves around. Not many refineries in the world are suiting for dynamic paths because it requires a very robust software and also workflow. So it is meant only for the very large refineries, and some of them do have the dynamic path algorithm. Then it comes to product preparation. Now, product preparation is also a tank mixer because material have to be mixed well before it is shipped out to the customer. And also for the incoming crude, because of the water in the crude, some tank mixers are also installed in the crude tanks. Then the tank recirculation, is usually done at the product side, like fuels, gasoline, diesel, and etc. Before they ship it to the customer, tanks are recirculated. Now, in addition to the blend header, which is also provides some sort of a mixing, refinery usually go to the tank circulation. Then the last one is the tank fugitive emission. That is estimated, not controlled, because when the tanks are loading, the levels are moving up, and the fugitive emission are released in the atmosphere, which has to be accounted for. Now, then infrastructure also have a terminal of operations for marine, truck, rail cars, and pipelines. And each of them have their own challenges. Some of are very critical, some of are small, and some of are medium. And you can see in the table on the slide, the demurrage charges are very high for the marine terminal because the ship is waiting and tanks are not available for unloading or loading, then they have a demurrage charges. If the products are not available in time, then they lose opportunities. So all these terminal operation are categorized under the management infrastructure. The truck terminal manages about 100 to 300 trucks per day, loading and unloading different products. So that has its own challenges. The rail cars and the pipelines. So I will not go into too much detail of each of this operation because that will cover in the different webinar in future. So these are the challenges for terminal operation in a refining industry. Next comes the product quality analysis. Now, there are many methods of analyzing a product quality before they are shipped to the customer. First and more traditionally is doing the lab analysis, laboratory. It works offline and it's a time delayed. So it follows a sampling and analysis schedule. Then next comes the signal quality discrete analyzers, which measures the signal quality at a time. it had been used for decades, but it was most expensive and mostly offline. And some of the refinery that I have experienced also uses today discrete analyzers. Then next advancement was multiplex multi-analysis like NIR, NMR. And they can analyze multiple qualities for multiple components. And this is where the refineries are installing NIR, NMR because they can be online um, for measuring the qualities of the components as well as tank. It has some limitation also, and we'll discuss a little bit more. Then there is a hybrid analysis system, which is also uses some lab, some model-based quality estimation, which is called inferential calculation, and an online analyzer. But the requirement is a little bit different, that analyzer have to be placed before the tank and not after the tank in most of the architecture for the analysis. Now we come to the blending system. Now blending in a refinery is the money making system because 80 to 90% of the refinery products are made in blending. And so blending can be done in different areas. Blending is done in the crude blending area where different crudes are mixed together, blended together to produce the blend which can be fed to the crude unit. Now there are two configuration for the crude blending. It can be pipeline to tanks and from tanks to the crude units. And we'll discuss this in a future webinar. Then it comes the fuel blending and the LPG blending. Now blending configuration can be many types. It can be batch, inline, rundown, with or without intermediate tanks. I've shown a few examples here on the slide that you can see. The third slide on the middle row is a rundown blending, which does the multiple header for diesel. This is the actual project screen I did for a Singapore refinery for multiple blend headers, rundown tanks. Then the last one comes important is the blend header. Typically the myth is that blend header is nothing but a piece of pipe, which is not true, because blend header plays a very important role in blending, fuel blending. Not only provides the mixing, which saves the energy for pump recirculation, but how the blend components are connected at the blend header in different order. And there is a webinar and also paper published on the concept of blend header design. Then the last one comes the blend tanks lineup. How many tanks are lined up for each component? Is it one tank or two tanks? And depends upon whether it's a solo tanks or a spare tank, the blending situation can change and it can create some challenges for the refinery. And we'll discuss a little bit more on that one. So the question usually I'm asked is that, okay, we have a very robust blending system, but how do we know that it has everything that the blending system is supposed to require? Is there any benchmark for that one? My company developed a methodology to benchmark the blending system. And it was done creating by two indices, which is automation effectiveness and operational efficiency index. First one answers the question, how automated are blending operations? And second one is, how well are blending operations executed? And based these two indexes, each area of the blending, each module of the blending is analyzed. And then we come up with the two indices, effectiveness index and operational index. And that translates directly into capital investment and tangible benefit versus return. So this gives refinery a method to decide which area of blending they need to invest in. And they can also compare from one refinery to another refinery for the same corporation or other corporation refinery. We have another webinar coming for this topic. Now, the infrastructure also requires the digital transformation. Now, you have seen and read on the internet that digital transformation is not quite done by each and every refinery. Still, they thought it's a luxury, but it's not a luxury. It's a necessary towards a profitable refining business. You can see in this slide that all the data on the process side, whether it's a quality measurement, fuel blending, data reconciliation, generates data. And that data controls the process. And once the process controls the data. So it's a both-way traffic. Process governs data and data controls process. So unless the digital transformation is implemented very effectively in refinery, is a potential of losing profitability. Then the integration. Refinery has lots of moving parts and lot of databases, lot of process flows and interaction from external and internal systems, including SAP, including yield accounting, including what happened at terminal, and they all have to be integrated together for increasing the profitability of the refinery. So these all constitute the infrastructure. So what do we take away from the strategic management of infrastructure? Refinery infrastructure implies that all is necessary for the refinery operation while focusing on the offsite operation. It's required that we refineries have adequate infrastructure in place to operate and make money for that one. Effective automation of refinery infrastructure precursor for the efficient controllability of the manufacturing of end products. Now, we cannot dispute the importance of digital transformation of process data for in-time decision making to sustain the financial survival. Now, we discussed the control of manufacturing. Now, control of manufacturing relates to tank inventory, loading, unloading, transfer, oil movement, terminal operation, single or multi-header crude blending, inline blending for the fuels, gasoline, diesel, fuel oil, etc., and also rundown blending for diesel, aviation, and kerosene. And there are many automation modules that you can see on this slide, which have to be integrated together because the information flows from one module to another module for integrated blending system. So let's look at the integrated crude blending system. Now, crude blending is done in two phases or two stages. First, the crude from the pipelines or any other means is blended in the tanks. And you can see this is from a real refinery in that the blending is done in tanks for the different requirement, different specs. And this particular refinery has 5 crude units, and each crude unit processes different types of crude. So the tanks, the first stage of crude blending is done in tanks to create crude for the different process unit. Now, second stage comes from crude tanks to crude units. And you can see this is a multi-header blender for the crude unit. And it processes the feed tanks of the crude to different spec. It's blended to different spec. Now, refineries also have implemented, not too many refineries, to integrate between the crude blending and the product blending. So you can see there's a feed forward and feed back. What kind of crude you want to receive and blend, and based on that one, what kind of a product a refinery can create from an end product point of view. So there is a very complex integration system between the two end, feed forward and feedback from a crude unit, crude blending to product blending. The oil movement system is also very complex because if you can look at it, there are about 13 to 14 different kind of activities of transfer from any source to any destination. But most of them is from tank to tank transfer, which is about 45 to 50% of all transfer tasks. And unit to tanks about take 30 to 35%. Remaining ones are small ones that you can see on the first chart on the slide. So two activities are constitute the major transfer tasks in the refinery. Then is integration of different module, different control for the oil movement. And you can see that has to be refinery-wide integration because the planner have to create an order for the transfer and has to be executed by the operations. Now, the number of movements depends upon the capacity of the crude unit or the refineries. This shows the 6 refineries with different capacities. And as the capacity of the refinery increases, the number of tasks on a daily basis also increases. So it's a direct function of crude capacity, how many movements are done every day. Now we come to blending. Traditionally, many decades ago, the blending was done manually using PLC, and it was tank to tank, one tank at a time. As the technology changes and the economics changes, then refinery started installing the DCS-based control. But that control was only for recipe control. It means somebody had to input the recipe in the DCS system, and DCS control, which is called regulatory control, was just to control the recipe. It did not do anything else. There was no feedback. There was no minimization or giveaway. There was no violation check. It was just auto start and stop and monitoring. The refinery, the recipe was designed by a planner, and traditionally those recipes were designed using Excel, using a linear model based on input of the lab qualities, and then fed manually or downloaded to the DCS. Now, I'm talking about this system maybe 15, 20 years ago, but the cost of the blending with no control was too much, and refinery started losing money. So they went to the 3-tier ultimate blend control optimization system, where the planning is done in offline optimizer, online control, and regulatory control. Now, there is a myth, and I mean, if I have talked to many refineries, they think that online blend control is necessary. No, it's not necessary. It's an optional system. It's optional because if you have a closed blend stock tank system, it means one of the tank is available to feed from the process unit while other tank is blending. That's a closed system. It means for that one, the qualities of the tanks, stock tanks are fixed. They don't change during the blending. And then for that reason, you don't need online blend control. But that doesn't happen. So most of the time, refinery do install blend control because the quality of the stock is changing. For the online control, there are many models. It can be used a model-based first principle, multivariable, neural or artificial intelligence network, index-based control, error-based control, and then third level is DCS-based control, which is regulatory control and DCS. So the 3 layers gives much better control of the refineries blending systems. Also, it minimizes the qualities giveaway and also minimize the office spec products. But there is something else missing here. In this system, the quality of the tank, the stock tanks are still could be changing if it's not a closed system. So what happens is, so there is a new advancement that the quality of the stock tank are monitored in real time. They are based on the model-based system, and they use the analyzers at the input of the stock tanks, and uses the lab analysis and online analyzers and historical data to update the biases in the quality prediction. So with this system, what happens is the planner always have the current tank qualities at any time. He doesn't have to wait for the lab analysis, which takes about sometimes 10 to 12 hours delays to plan the recipe, and the production can increase of the blend because he can plan better and in real time. This is the latest configuration of the blending system, which overcomes many drawbacks. So what is your takeaway from the strategic control of manufacturing? Now we know refinery makes 80 to 90% of its end products in the offsite operation. Hence it requires very efficient controllability of product specs. Fuel blending is a critical operation to improve refinery's bottom line, and hence must be robust and updated. Crude blending plays an important role to make sure the crude available to the crude units to make end product on spec. On-site operation is a continuous process, whereas the off-site operation are discrete or batch processes. Now, let's look at optimization of production. We had talked a little bit before, but we'll re-emphasize again. So the optimization production is refinery-wide LP optimization, which is done by the carport planner or refinery planner. It does the crude procurement and supply planning and scheduling, single or multi-header crude blending, oil movement, path selection, inline blending, rundown blending, and optimization of tank utilization. Because as I talked in the last webinar, there is a billions of dollars of liquid assets staying in the tank form, and the more they stay as a stagnant inventory, refinery loses money. So they have to optimize the utilization of tanks and its inventory. So let's look at blend models and optimizers. So if you look at the crude blending, there are different types of model. It can be linear, linearized, index, or non-linear. Now, crude blending is a linear model. It doesn't have a non-linearity because controlling 2 to 3 qualities, which is sulfur, API, and PNA. And I've shown a optimizer which is based on Excel, that it is optimizing four types of blend: light sweet, medium sour, and heavy sour, and it gives the profit potential. This can be used by usually oil traders, or also can be used by refinery to decide on the purchase of crude oil. The fuel blending. Now, fuel blending is a very complex system because it has interaction between the components. It has models for many qualities, and it has to be optimized. So in terms of optimizer, there are linear, non-linear, multivariable regression, which is usually used for crude blending, linear programming LP, or successive linear programming LP, or non-linear programming non-LP. The interface can be Excel, VB6, Fortran, or ASP pages. And you see in the market a lot of blending optimizer for the offline and online. And basically at the back end, all are basically using the same models. Sometimes they use any of the first principle models, or they do the blend control or error control and other things. So on the fourth slide, the bottom right, you will see the butane blending. And the next webinar is on the butane blending, how the butane can be economized between the LPG blending or a gasoline blending. And we'll discuss more of this in the next webinar. The blend model I talked about it has a different flavor, like a RVP model or dew point model for octane or distillation point model. Now, these are generic model prevailing in the industry for decades, and it depends upon what models are used by the refinery. Now, RVP models and distillation models are pretty common. The difference between dew point model for octane is the most robust because you use the interaction between the two components, and you will see later as the component interact, they can change the quality of the blend. These models are only generic. They are not customized to the refinery. So refinery have to make sure that all models are customized for their parameters. And that can be done using a historical data or blend data. Methods for updating the parameters can be manual updates, like for dew point coefficients. Now, dew point coefficients are very tricky and very labor intensive. It's not done every year. It's done every 5 to 10 years because it requires taking a sample and preparing the samples, measuring the octane of individual sample points, and then mixing them. So it's a very time consuming and very labor intensive and costly. OMS had developed a non-invasive methods to estimating the dew point coefficients, and we'll discuss it in few webinars. The backcasting, offline regression from history, real-time regression for feedback. Now, one thing I want to make a point here, that offline optimizer can use only the first principle models, the blend models that you see here. Online control can use many other non-model techniques, but offline optimizer has to use the first principle model based on equations. So the blending has errors at many points from end to end. This slide shows the sources of errors. Like if you look at the in point, the analyzer transport lag, analyzer dead time, and then blending model errors, and then the prediction at the header time, and their analyzers errors, and model bias calculation. So this entire picture shows you the sources and the method to correct those errors. And all we are doing correction of errors, blending to predict the blend quality better. So we don't end up giving quality giveaway or violate the blend specs. But that's not enough. Then we put a bias term in the equation even after correcting all the source point that we shown before. And then bias has many terms. It can be from the lab analysis error, online analyzers, predicted blend header quality, or final blend head qualities. And there is a method how to estimate each of the bias terms. And then we have a lab analysis errors, which is done by round robin method, and the backcasting method. So there are many techniques and methods available in the industry, and refinery using some of it, if not all, to correct the blend errors just to predict the quality better. And we will discuss some of this concept in our webinars. So watch for those webinars. This is a typical example of the effect of component interaction on blend quality. And dew point coefficients shows clearly that it can be boost in the octane or penalty. What I mean by that, if you take two components, like first one isopentene and isomer blend, and vary the percentage of isopentene, the blend could have the boost, and it could be boost of about 8 to 9 octane. On the other hand, if you do isopentene with the FCC blend, it can have penalty. It means the ending blend could have decrease in octane compared to its components. So this is very important, that how this component interact with each other to affect the quality, especially the octane of the blend. If we don't have the correct coefficients or correct interaction, then it could either give away or it can violate. And you can see at the bottom two graphs that if you use a different model, the blend quality can move towards the giveaway or towards the right. But if you use the dew point coefficient correctly, then it is a normal plot. So our takeaway from optimization of production. Optimization of production is very important because it ensures that products are manufactured with products on spec and at minimum cost of production. It's not only minimizing the quality giveaway or minimizing the office spec products, but also to gain financial tangible gains. It is required that all sources of errors are identified and correct offline or in real time. It requires a skill. Now, fuel blending is in my opinion, is the area where it requires skills, because it has to analyze it, correct it, and make the next blend. And it's not something that without proper training can be handled casually. So refinery must invest in human capital first before realizing the financial gain. And human capital, I mean, is the training the staff in optimization of production. The last strategy of MCOR is reconciliation of hydrocarbon. Now, I have discussed this a little bit detail in the previous webinar, but it has three areas: fence line balancing, unit balancing, and hydrocarbon balancing, which is oil loss. Now, fence line balancing is reconciliation of received orders and dispatches. So the refinery have to balance at the terminal site, fence line receipt and dispatch. So if you are receiving the order from the vendor, then you have to match what they placed the order and what they received. And sometimes there's a discrepancy. Discrepancy can be at the vendor side or it can be at the refinery side. On the dispatch side, what order you receive from the customer and what you ship them out, it has to be balanced out. I was consulting a refinery in US, and the financial manager told me that sometimes they have lost $100,000 in one shipment because they were not reconciled. What customer said they received and what refinery said they sent, they were not reconciled. And that was mostly in measurement of fence line on either customer side or refinery side. And sometimes it can have a legal entanglement. Then we have unit balances. Now, the unit balances is basically a meter reconciliation. And that's very critical because it affects the unit performance. If the meters are not calibrated, the process units could be manufacturing a different quality because the set points are not matching the flow rate. And it could affect. And also what is sending to tanks from the units, they have to reconcile. So this is something unit balancing. Then hydrocarbon balances between transfers, slope, chemical loss, unaccounted loss, and internal usage. Now, fence line balancing, I said before, at the 4 terminals: marine, trucks, rail cars, and pipelines. So the fence line balancing defines the battery line of all terminals. It balances the receipt and dispatches, and it requires the correct measurement of the transfer and receipt by custody transfer meters. And so basically it amounts to what comes in and what goes out across the boundaries. It amounts to knowing exactly and accurately the dispatch and receipts. Now, fence line balancing also looks at the opening stocks and receipts and closing stocks and shipment. And this is basically more of an oil movement system. If you don't have an accurate engaging system or it's not done properly, then even 0.1 difference could means thousands of dollars. And you will see in the next slide, loss to the refinery. So once the fence line balancing is done, it goes to the process unit balancing and losses. And here, the only process loss are measured is the transaction or controls by the process units. Everything else is what refinery is consuming for its own use, or what can be accounted, what cannot be accounted. And then at the end, it becomes oil loss percentage. Now, typically, it's a 0.5 to 1% oil loss industry average, but I've seen refinery which have measured 4 to 5% losses, which is not realistic. Give you an example of what happens when you do the tank-to-tank transfer and the error in measurement. This tank has an open inventory and a closed inventory, and it receives and sends out, and there is an error 0.05%, and it amounts to 67.5 pounds. Now, in each transfer, if it is that much error, and if you multiply by 300 transfer every day and then kind of error, the financial loss accumulates on daily basis. And my consulting with the financial managers of a refinery, they confirm that's the biggest problem of the reconciliation hydrocarbons. So they emphasize on the accurate measurements across the refinery, and they spend a lot of money on accurate measurements. And this is a difficult calculation errors and lack of accurate measurements. Now you can see the gain and loss across the refinery. Now, one thing is critical here, that loss is not measured in terms of volume, it measures in terms of mass. And here, these two actual refinery cases showing that the mass is gained instead of lost. This is a alarm because, and they show this because of calculation error or because of measurement error. So refinery look at this thing and say, hey, something is wrong, and then they correct it. But this is a alarming situation. Oil loss can be improved. So if you improve the oil loss by 0.5 sigma, a very conservative approach, and I have done this for refineries in the US, and you can see the benefits of reducing the oil loss. It can vary anywhere between $1 million per year to $8 million per year, depends on the capacity of the refinery. So the oil loss or reconciliation of hydrocarbon is very important for refinery to maintain the profitability. So to take away from reconciliation of hydrocarbons, at the end of the day, it only matters how much and how accurate is the refinery oil loss. The oil loss reflects on the end-to-end strategy I discussed in this webinar. Refineries struggle to create a perfect reconciliation of hydrocarbons and workflow, but they still miss out in the end. It's not a secret that a skill gap and lack of management commitment to implement automation results in a poor oil loss. Let me give you a case example here. I work with a refinery who automated entire operation of reconciliation end to end, and every step was automated. But after 30 days, they gave away. They gave up because the workload was too much and the benefit gain was very little. So it's important to balance it out, how much you want to work to reconcile the hydrocarbons and what automation you can put in place without burning out yourself. Okay. So how do we estimate this tangible benefits? I think I missed the slide. Let me go back. Okay. There are many methods of estimating the benefits. There are some very inaccurate methods and also accurate method. I have done the analysis by 4 different methods. Email me if you want a copy of this one. And then octane blending tangible benefit calculator. When we are changing from 87 to 92 or 95, how much giveaway we are calculating. It's a simple calculation and algorithm behind it which can give you, this is more accurate. And you can see the third method, you can see that we take the historical data and giveaway and then plot them a normal plot, and we can estimate the giveaway benefits. The fourth method is which I did for refinery in US is that we took the 30 days or 90 days of blend historical data and we optimize each and every blend using the optimizer and see how much money they have lost it, and results were out of this world. I mean, they were losing millions of dollars, almost every month on suboptimal blending. So there are different methods of estimating blending benefits. This gives you a little bit of estimate of different areas of tank form and oil movements, and these are the numbers from the industry and also some of our OMS consulting experiences. We can relate this into 4 MCOR strategy that we talked about it in this slide, and we can say the management of infrastructure is 7 to 15 million. Then comes to control manufacturing, which is 5 to 10 million. Optimize is the maximum, which is 20 to 25 million because it involves the good fuel blending, reconciliation, and staff training. 1 to 2 million per year they can be saved. Finally, I would not play low on the aspect of training. Now we can do everything in MCOR strategy, and we can estimate and all the benefit. But if staff is not trained, if there is a skill gap, all the benefit and all the calculation done is no use. So the staff has to be trained properly, and because revolving and so many situations last 2 years, the staff feel that they are trained. There are different methods: in-house training, public courses, online courses, e-learning courses, which our company provides it. They have a pros and cons for each of the method and the cost involved. So I cannot emphasize enough that training is very important. If you look at some of the discussion on internet by McKinsey, and I think they say the skill gap is becoming a critical factor in the industry nowadays. And if you look at the cost of the different types of refinery training, you can see the e-learning courses gives the least cost and also offers the maximum number of training courses. So in summary, MCOR strategy uses divide and conquer principle to create effective infrastructure, efficient manufacturing, and profitable reconciliation of hydrocarbons. Offsite operations are complex and workforce intensive from both skill levels and responsibility point of view. Refinery management commitment is critical to invest human capital as nature workforce is changing with time and age staff retirement and work from home culture after pandemic. Downstream refining is declining in profit margin for various controllable or uncontrollable factors. Refinery management must invest in technology and people to regain in the margin. Our next webinar on December 8th is we talk about economics of butane disposition, and I have a co-speaker, Tom Edwards, who is the president of Technique, and please I invite you to join. This is the list of the webinars that we have scheduled for next 12 months. Keep a watch on registration. We'll have 2 poll questions after this, and please give us your candid feedback. Please stay. This is the end of my webinar. Please stay for a few more minutes to start the question and answer session. Melisha?
Thank you so much, everyone. I will go ahead and launch the poll questions. Please go ahead and take a moment and respond. I'd like to thank you all for joining us today. We do appreciate you taking time to join us today. Again, please go ahead and respond to the poll questions that have appeared on your screen. And then this does conclude today's webinar. Once you complete the poll, you are free to disconnect. Thank you so much, everyone.